Hi, everyone. I'm Aditi. It's a great pleasure to be here. I work broadly on robust and reliable deep learning. And today I'll talk about some of the failure modes that happen in neural networks and what we can do about it, given that they don't really learn causal mechanisms and hence they're like, they can get affected by spurious correlations. Okay, so as many of you all are probably aware, neural networks are the workhorses that have powered some of the most impressive advances that we've been seeing in AI, for example, like AlphaGo and GPT-3 and so on. Every once in a while, purely for my entertainment, I open GPT-3 and I try to see what it does in certain things. And so this time I asked to explain to a 10-year-old the first line of this workshop, and it actually did a pretty reasonable job. Like it explained something about causality, like what TCS is about and how we want to bring everyone together to make things that are more robust or less likely to give incorrect results. So, well, this is by no far like the most impressive application or anything, but this is just for fun. But we see that neural networks have actually enabled pretty impressive advances, and so a lot of people are excited about using deep networks to solve many problems. So the usual pipeline to do so is to collect some training data, like a lot of training data. And then you pick some kind of the latest and greatest model architecture. Then you put them together and you have some objective to fit this training data. And then you get your final model parameters. And so like the obvious issue here is that your training data could contain a lot of correlations, some of which are useful, some of which are not useful or meaningless. And these are going to show up in your model. And this turns out to be a real problem. And I think it's one of the biggest challenges that we have in using these highly predictive models in practice is that you don't know how to evaluate these models because they do fit your training distribution well, but when you actually deploy them, things can break because you're deploying them in new environments or new populations where some correlations don't hold up. So as an example, this is an image of a chest X-ray, and let's say we're trying to use machine learning to help us determine whether it has a collapsed lung or not. And you can do the usual collect a training data set and train a model. And people did this, and it turns out you can do quite well. For example, on the held out test set, the accuracy is pretty high, and it correctly classified that this image here is a collapsed lung. But upon further examination, it was found that actually why the model made this prediction was because of using this treatment, which is this tube on the X-ray here. And so in the data set, when you collected all the patients who were identified to have the collapsed lung all also received treatment. And so there was this spurious correlation. And so when people actually tried to deploy this model, it didn't really do anything at all because it cannot detect untreated collapsed lungs. So here's one example of how certain correlations in a data set seem to be useful for making predictions, but you don't really want your model to use them because they're not going to work when you use them. So there are many other such examples, they can be pretty catastrophic as well, like a self-driving car ended up killing a woman because, among other issues, it was only trained to recognize pedestrians at crosswalks. And so when there was a pedestrian who was jaywalking, the model didn't know you had to stop because it assumed that you were only stopping for the crosswalk and not the notion of a pedestrian. Okay, so the way I view it, I think the fact that you have these neural networks that they're these giant models that can pick a lot of complex patterns from the data set, you don't have to hand engineer features. And that was kind of the main selling point and why everyone's excited about it, because you don't have to sit down and come up with good features and the models are picking up something. But it's a double-edged sword because sometimes you have no idea what the model is picking up, you can't control these. And so this can be pretty challenging when you want to say that certain predictive features are what you actually want the model to use, and you don't want it to pick anything and everything that it finds in the data set. So in this talk, I'll kind of talk a little bit about how we can try to enforce some structure in what these neural networks do end up learning. We're looking at a very simple starting case where certain attributes in your data set, they're correlated, but you just don't want your model to pick that up. How do you actually train a network to obey that constraint? Then I'll go a little bit and I'll use that as a starting point to talk more broadly about where we think the research in neural networks is going to go and how do we bridge this gap between them not learning causal structures, but still want to retain their predictive power. So with that, I'll jump into the first part, which is on removing known spurious correlations from your data set. So first, I'll discuss the setup and evaluation, and then I'll try to come up with a story about how we can fix some of these issues. Okay, so just to recap, models do latch on to spurious correlations like we saw in the chest X-ray, where these are misleading heuristics. And so, if, for example, if it held up on all of your training examples, maybe that's impossible to disambiguate at all. So let's assume that they don't always work. So there are some points in the data set where it doesn't work, but like, how does the model actually perform in such a situation? Here's a simpler example with like fewer medical terms. So this is an image of a bird. And let's say we're trying to train a model to decide whether it is a water bird or a land bird. And as you've probably guessed, there's a spurious correlation in the background because most water birds occur in water and land birds in land. And if you look at the average error, it looks pretty good, like 3% if you use a good neural network. But the model is actually using the background to make its predictions. So if you have an image like this, where the bird is actually a water bird and the true label is water, things are fine. But if you have an example, so things are right in this situation where the background is actually matching the label. So even if the model used the background to make its predictions, things are fine. But if you have an image like this, which is a water bird in a land background, the model is going to use its background to make its prediction. So even though this is a duck, it's going to say that this is land because it's detecting the background. And so in such examples, the model makes a mistake. And it's not just as one example, like on aggregated over the entire data set, the model gets 40% error on such examples of water birds and land background because it's predominantly using the background to make its predictions. So here is a setting where, we know that background is a spurious correlation, and there is a lot more signal in the foreground that the model should be picking up on. And so we're trying to look at how do we get a model to actually do that. So the way we set this up is that, let's assume it's binary classification for simplicity, and that there are two kinds of backgrounds. So your spurious attribute can take one of two values, and your label can take one of two values. So we can construct a 2x2 grid depending on the attribute and the label for each of the data points. So most of your data points have the background matching the label, like water birds found in water background. And this is an example. But there are some minority points where sometimes you do have these situations where there's a bird in a different background. And so those are the minority points. So in this way, we can put each input into one of these four categories. And for now, we're assuming that for each input, we can't say what the background is and what the label is. And so we can put them into these four categories. So now we can look at what is the error of a model that is just trained on a data set with this kind of a distribution, and what does it do? So it gets pretty good performance on the majority group. So it gets like 5% and 0.4%. But you can see that it has very high error on the minority groups. So the average error is pretty good. But the error on the minority groups is really high because the model is using the background to make its predictions. And so it gets things wrong where the background doesn't actually match the label. So viewed in this way, this is convenient because now this tells us that what we want, if we want to say that the model does not use its spurious attribute, is that we want to train models which have small errors on all these different groups. So if you have a model that gets good performance on birds irrespective of their backgrounds, and that says that the model is actually not using the background. So this is so we set this problem of removing spurious correlations from the data set as one in which you have different groups in your population, and you want your model to work well even on groups which are the minorities. Yeah.
How do you know which group the photo falls into?
Yeah, so in this situation, we're assuming that we can look at, so this is actually this particular data set is synthetically constructed. So you do have that attribute of the background and the foreground. And some other data sets that we run these experiments on, we have the meta information on what the attributes are. But if I have time in the later part, I'll talk about what we could potentially do if we don't have that information. Are there any other questions so far on the setup and evaluation? Okay. So now, viewed that way, we want to improve the worst group error. And the natural strategy is, you have a data set in which there are different groups. And so some groups are minority, your model is doing badly, there is some imbalance. And so the natural technique is to reweight the loss based on different group proportion. So what this means is that there are a lot more examples on the majority. So what we'll do is we will reduce the weights on those points in the loss and we increase the weight on the minority points. So this is an attempt to get the model to really pay attention to these minority groups and not just ignore them, or like because they're just a few of them, don't get a high loss on them, like really try to get it right. So this is the natural objective that we could try, which is to increase the weight on the groups which are small in size. You could do some slightly, yeah, sorry.
They can't see the slides anymore on. Someone goes with that.
Oh, okay, great. Was it something? Did I do something? Okay, no, let me know if that happens again. Okay, so so this is kind of the natural strategy, but you could do something more sophisticated as well, which is like, maximize, like do some robust optimization, which is to minimize the worst case error on your training data set, because that's kind of the objective you're measuring on the test set as well. And as I'll show in the next slide, we'll look at how these methods work. And these like robust optimization performs pretty similarly to increasing the weight. So I'll just focus on this upweighting approach because it's more intuitive. Okay, so with that setting, we can look at what happens when we actually try to train these models with this reweighting. This is the same bird example from before. So this is the visualization of the performance as you increase the size of the models. So the parameter count is basically the size of the models. So I'll walk through all these lines. So first, let's observe the test error, which is like the average test error. So we're not accounting for any like group information. We're just looking at the average performance on the test set. So we see that as we increase the size of the models, the test error goes down. And actually, you get pretty good test error for large models. And so for people who are familiar with deep learning, it kind of confirms the trend that we're familiar with, where if you use larger models, the performance is better. And right now we have a lot of push towards using like trillions of parameters or something. So it kind of matches the common wisdom here. But if you look at the worst group error, we find something interesting, which is that the error first goes down and then kind of goes up again. And so if you look at the largest model, it actually obtains a pretty high worst group error compared to the smaller models that are somewhere in between. So this was pretty surprising because this is quite like we never see such graphs typically in machine learning if you look at the literature, because all the graphs look like the the black graph here, and it's called the double descent phenomenon, where you having larger models actually just works better and you don't have an overfitting problem. So if you look at the worst group error, you are seeing that well, actually overfitting is a problem and using smaller models is better. So just to make sure this is not an artifact of this data set, we can look at other data sets as well. And yeah, this is a slightly weird application, so pardon that, but you're trying to detect hair color and from the celebrity data set. And turns out that gender is a spurious correlation because in the data set, most of the women celebrities have blonde hair. And so if you look at the males with blonde hair, they're actually less than 1%. So I know it's slightly weird to call them a minority, but that's what it was in this data set. So we see something similar here, where the black curve kind of goes down, and then your blue, the worst group error, does increase as you increase the size of the models. So this got us interested to think about if we were really trying to reduce these spurious correlations, and this is a dead simple case where you knew what the correlation is, you knew what each data point was, but still if you just train the largest model, you can't do well, and you kind of need to rethink regularization and how do we train these models. We found that increasing model size actually increases the worst group error. So now I'll present some explanation for why we think this is happening and what that tells us about how do we actually fix this problem in practice. So when is it this case that having large models does worse than having small models? In the paper, we analyzed this, the paper here in ICML 2020, we analyzed a high dimensional linear setting. And I'll just have an informal simplified version here. So we find that we can prove that the worst group error is high when the following two conditions hold. One is that the spurious feature, which is the background, is somehow easier to learn for the model than the complex, the foreground. So actually looking at the features of a bird to determine what the bird is something much harder to do than just looking at the color of the background, for example, that pretty much tells you whether it's land or water. That's the first condition. And then the second condition is that if there are a lot more majority points than minority. So If you were in a situation where like you're equally likely to see a bird in any background, then the model is not going to pick that up. But in reality, it is going to be the case if you just collect data that a lot more water birds are going to be in water. So if this condition holds, then we find this observation. So here's a pictorial description of what we think is happening here. So let's say this is kind of what the data look like. So you have some land and you have some water. So a lot of the examples are actually like water birds in water background. But there is this one example potentially, or like minority example, that there is a water bird in a land background. So now if a model just used the background to make its prediction, it is going to get this point wrong. And in fact, we upweighted this point. Oops, sorry. In fact, we increased the weight on this point to precisely prevent something like this from happening, because this kind of a boundary would have a high loss and the model is going to get it wrong. And it's going to suffer a high loss as a result of upweighting. But the problem is when you use a large model, you don't really have a control on like how the model is going to learn. And one thing that could happen and we observe is that the model just kind of overfits to this particular training example and does something complex and learns a boundary that doesn't really generalize. So because you have a large number of parameters, something like this can easily happen. And this is kind of what we observe, why the training loss is still 0. And so you do fit this particular point, and increasing the weight or not doesn't matter because already the loss is 0. But the reason the loss is 0 is because the model is doing something degenerate and doesn't really generalize. So what we find happens is that the model could fit this particular point without generalizing to the test set. And this should actually not be that surprising because when we think about having a large capacity, and traditional statistics tells us we should be doing regularization and this could be a problem. But somehow we don't see this if we just look at the average error, which leads us to believe that we can't just use the largest neural network we find and things are okay. But if you look at this kind of a voice group error setting, this becomes a real problem. So what we find is that large models can actually cheat and like overfit to get these minority points right. And just increasing the weight is not going to solve this problem because anyway, it already has a low loss. And empirically, we find that it is the case that increasing the weight does not really solve the problem of spurious correlations when you have a large model. In contrast, let's look at what happens with small models. Of course, if like models are regularized and they have a limited capacity, they can no longer do this like cheating. So this is what your data set look like. If the model used the background to make its prediction, it is going to get a high loss on this. It is going to get this point wrong. And we have increased the weight on this data point. So it's going to like suffer a high reweighted loss. So its objective is going to be high. And it can't do this complicated like, boundary around this particular data point anymore. And so if it has to get a low loss such that it fits this particular training point as well, then it has to do something that doesn't exclusively use the background. This shows why small models, especially when you reweight them, you can actually control the kind of boundaries they learn to say that it gets everything right. And now you don't have the problem that they're going to just cheat and overfit, and it can actually learn something more meaningful. What we find is that in this case, like by using small models and by regularizing appropriately and upweighting the minority points, we can actually solve this problem and get low voice group error. Are there any questions? Okay. So with that like kind of theoretical understanding, we try to see if there's anything else that we could do in using large models, or should we just give up on using large models because kind of that's what people usually do in practice though. So we looked at, can large models ever obtain low voice group error? So the two contributing factors from the theory is that the core feature, that is like the bird features in some sense, are like harder to learn than the background. And there was this group imbalance. So this is inherent to the data set. So we can't really change like which features are easy to learn or like what the features are. But this group imbalance is something that maybe we could do something and control via like collecting the data set carefully. So what we were wondering is whether we can reduce this group imbalance by just removing a lot of majority points by subsampling. So what this means is that initially we had a data set that looks like this, where you have a lot more examples in your majority and a few in the minority. And in this case, like we tried to just reweight these points, and that didn't help if we were using large models. So instead, what we're saying is like the theory tells us that like if we didn't have this group imbalance at all, then things will be fine. And one way to do that is to just remove a lot of majority points, and that's what we call subsampling. So initially this was a bit strange because especially in like some of the data sets that we have, this would end up meaning we remove 90% of the training points. And like removing training data is just never a thing that people would ever think of doing because it feels like data is just always helpful. Anyway, so we'd like, this is pretty counterintuitive, but our theory said that this should help. And so we're like, let's just try and see what happens. And I guess because I'm giving this talk, it probably works. So what we see is that, so this is the figure from before where you're using the full data set. So the worst group error like first decreases and then goes up with large models. We now use a subsample data set instead. We see that now both the average and the worst group error go down as we increase the size of the model. And you're back to kind of the familiar territory where large models are better. And so now like large models are actually able to get like, much better error than before when we were using the full data set. So it's kind of surprising that like removing a lot of data actually helped solve this problem, but that's what we observed. So we observed something similar on this celebrity data set as well, where originally large models were worse and doing badly, but with subsampling, large models are now working better and like kind of match the performance of the small models with full data set. And the average error also goes down, which is like kind of what we expect. So we find is this interesting observation that removing majority data improves the worst group accuracy of large models. Yeah.
If those graphs on the right, they're on the same y-axis.
Yeah.
Then is it true that the best the subsampling can get, it still looks a little bit worse than the small models if I just reweighted? Is that true?
Yeah. So I think this like they're comparable. Like this is like on this particular graph it is lower, but like if you do it a little more carefully, like tune parameters and like use slightly different models, we were able to bridge the gap. So it's not like I don't think we can conclusively say that reweighting with small models is strictly better, but like in some cases it is. Yeah.
So could you also hope for other kind of interventions on the loss function? Because the loss, maybe it shouldn't be symmetric or independent of the background. And then there could be ways to use the whole data set, but bias it.
Yeah, so I think people have tried to do something like looking at the salient, like some recent work that I've seen where they try to look up the saliency maps or like the gradients and say that the gradient should be like more aligned with the foreground or something. So like you kind of segment out the foreground and then say that the gradient should be aligned. That's, I guess, is that the kind of thing that you're saying?
Also, I mean, if you have the protected label of like what the background is, your loss function could be worse if it's from a minority group. And then you could also, penalize it. So you could still hope for the same kind of downward slope for the worst case group accuracy, but in a way that you can still use the full data set.
Yeah, I think one thing that I've seen people try is to increase the margin, like basically change the exponent in the loss such that you're requiring higher margin on the minority points than the majority points. In principle, that should help, but I think we don't have a very good way of like mapping our notion of like what these networks are doing in terms of like how to prevent memorization to like a loss. If you had a right way to do that, I think it should work in principle. Yeah.
So the black lines have gotten worse, which you would expect because you have reduced the data set size, right?
Yeah.
So that is
a problem. So even if you don't reduce the data set size, you're black. Like if you look here, like if you take the best performing model, your like black line is still higher than here. So this seems like, this is one of the other issues when trying to do any robust training, which is that because you're forcing like learning the foreground is actually much harder. And so if you have an image in the test set where you could have used the background to get it right, but now it's like a complicated bird and the model is like kind of going to get it wrong. So it's a bit tricky where like you kind of want the model to use the background only if the foreground doesn't have enough signal, but it's not clear how do we get models to actually do that. Yeah, so for this particular setting where synthetic, you can solve the problem by doing that. But I guess in practice, you'd imagine that we don't really have a good generative mechanism. But maybe with the progress in generative models that we have, like I don't know, it could potentially be possible that we can do some kind of controllable generation to help with this problem. Yeah. Okay, so let me summarize this part. To start with this observation that large models can actually have high worst group error. And so even if you try to remove a particular spurious correlation that exists in your data set, you can fail. And the core issue here is that these features, yeah, so yeah, basically your, oops, there's a typo here. Like the spurious features are easier to learn, and there's kind of a group imbalance that leads to this problem. And a theory, like a fix based on kind of this understanding is that we can't change the features, but let's change the imbalance, and kind of subsampling helps. I wouldn't really call this a fix. It's just like kind of checking that this intuition makes sense. But this is at least one way in which we can have large models to have low worst group error. But like, many of you observed, you're actually sacrificing a lot of data to use large models. There is kind of this interesting dichotomy that either we're sacrificing a lot of data or we're sacrificing a lot of capacity. And so, clearly there's something better we can do, but we don't have a way to do that with our kind of current deep learning understanding and pipeline so far. Okay, now is there any questions before I switch to the next part?
Oh, I had a question, which is, I guess so the formal theorem, we saw like a high level version of the theorem, but I think that the reweighting that you're using is fixed. It's this like class and balance. So something like, I presume, like 1 over the class size.
Yeah.
And so then I'm wondering about different types of reweightings that might depend on the complexity of the model. And if you guys have thought about something like in that direction. So instead of keeping the weighting scheme fixed, changing it as the model gets like more complex.
Yeah, I see. We did not try something with that. Yeah, I don't have a good intuition of whether something like that would help, because in practice, it's not so like if you just take a fixed model, its performance is not that sensitive to like what's the exact upweighting factor, but like, yeah, in like a small range. So yeah, so my initial intuition that it might not work very well, but like this, you could get some gains. Yeah. Okay. So kind of popping back up, like, so, right now I said that like these networks pick up the, like we saw one quick example of what's going on. So like, what's the broader story of why networks pick up on certain correlations that exist in your data set? So one of the disadvantages of just collecting a lot of data and throwing it at your model is that there are a lot of features that are actually predictive, but only some of them are reliable. Like for example, if you have like only causal features in your data set, that's great, everything's going to be reliable, you can just use it. But that's not going to be the case if you just don't think about the features and give it a model. Oops, wrong, last minute animations. But yeah, so ideally we want to only use reliable features, but this was the it requires information about which features are reliable. And one thing that we found interesting was that like this is a very pervasive phenomenon. And so like on most data sets, we find that neural networks often use only these spurious correlations. So it's not that they use some amount of the background, but they're pretty much always exclusively using the background or like some kind of texture to make its prediction. And so it's like these are a real problem because they, not just that the models use them, but they use them a lot more than the meaningful signals. So the general kind of story here is that whenever these spurious patterns are simpler to learn than reliable ones, which we find is quite a lot in practice. So for example, detecting whether a tube is present or not is of course a much easier task than like actually seeing if it's like, collapsed or not. So whenever you have anything like this, then the model is going to just use the spurious correlation. So we try to like, generalize this a little bit. And so we had this simple, and we thought about, let's try to attack the core issue here, which is how do we overcome this kind of a simplicity bias of neural networks in general? There's like a synthetic data set that we created that I think was interesting because you can prove stuff and also see what's going on. So if you had like a spurious feature and a robust feature, so you see that both of them give you some information about the true label, which is like blue or orange. So if you're doing some kind of a max margin or like trying to do the best thing that we could with this data set, you should be learning something like this, which is using some information about both the robust and the spurious features, and this kind of keeps these points far from the boundary. But what we find when we run experiments is like on all these different neural network architectures and across many different learning rates and everything, you basically always learn something like this, where the model is just going to use the spurious feature. So it's going to learn this green boundary that separates a data set, even though it could have learned something that separated your data set much better, because it has the capacity to express piecewise linear functions. And you could argue that that's not like it's okay, because like this was still working on your data set. So why should the model be doing anything more? And so we made this more noisy such that the spurious feature is no longer perfect. And interestingly, we see that the neural network still learns only the green boundary. But basically, if you have points like this, just like the land bird in the water example, they're just going to be kind of memorized in the sense that they don't really like the network is just going to do something local along this part, instead of actually using that information to learn the better boundary. So this is kind of interesting. It says that if you just collected a lot of diverse data on its own, that's actually just insufficient. So you could have been very careful about ensuring that you capture all the different points in the tails that could happen. And you just collect a lot of data, you are going to see a bunch of the tails. But that's just not sufficient, because if they're like not present with high enough, if they're not present with high enough numbers, the network is still overwhelmingly going to do the simplest thing. And so kind of, with like all this intuition, we tried to think about what we could do potentially if we just didn't know exactly what points to upweight. So this was the recipe from the first part of the talk, which is if you knew what points to upweight and then you kind of regularize your network carefully, you can ensure that you're not going to memorize these particular important points and you're forcing the network to learn something useful. But this was, like we knew what points to upweight because we knew kind of this is an image of a bird in like a different background. And so that's likely going to be important that the network should pay attention to. So now we ask, can we identify these points automatically with a little bit of understanding of like why networks pay attention to certain points and not others? With this kind of a simple idea, which is that, so we observed that, so there are these important points in a data set, but your model is not learning from them, because we call this informally memorization. And if you look at the neural network training, this kind of happens later in training. So so like it first learns something linear and then kind of spends its time fitting those points which don't match the linear pattern. So that told us that if we could somehow stop the network when it just learned the linear thing, and then look at which are the points it gets wrong, those are probably going to be the points that the network would have eventually just done something degenerate on. And so if we could pick them up and upweight them, then maybe we can get the network to learn something better from these points, rather than just letting it to continue to train and do something silly. So this was kind of the intuition that, because harder to fit points are the thing that the network misses out, let's identify them by just training a network for a little bit, seeing what it gets wrong, and then upweighting them. So that led to this kind of two-step process where we first train a model for a few iterations so that it doesn't, overfit and doesn't do these complex patterns. We use that to identify misclassified points. Now, these misclassified points are probably going to be the important points. And so in the second step, we upweight them and then we regularize. And like from the kind of understanding from the first part of the talk, this should actually do something useful because we're regularizing carefully. And from the, and because these points are likely to be important points since the network gets wrong, we kind of hope that this helps. So this is very, very important caveat that we found is that we didn't know how to figure out like when to stop training, like what is a simple enough model. And so this did require like some kind of cross-validation that leaks some information about the groups. So this is not a perfect solution, but like empirically it does reduce the number of points on which you need to know what's going on. But this gets at something that you could try to heuristically do to, if you didn't know which points are important, is to like use the network itself to tell you which points are important. We kind of tried this on these data sets, and it does better than just standard training, but it doesn't really match what the best you could do if you had perfect information on which are the points that you want to use. There've been a lot of other recent works as well that kind of try to do something similar, where you notice the points that the network gets wrong and try to get the model to pay more attention to that. And on this other data set as well, it's kind of similar. So it works better, and it gets like about 80% of the gap is covered by just this simple idea. This is not a perfect method in any means, but it kind of gave us some hope that maybe there is something that you could do potentially, even if you didn't know everything about what you want to remove from your data set. Okay. So to summarize, having diverse data on its own is not sufficient to ensure that networks learn reliable predictors. And so this seems like an obvious starting point is like, let's assume we have diverse data, but unfortunately that's itself not sufficient. But like maybe there's still something we could do based on understanding like what is it that these neural networks pick up and how do we make sure that they are using all the diverse data points in the right way. So this requires some regularization of capacity, which is interestingly contrary to the current trends. I think people should be thinking more carefully about just using bigger models and throwing a lot of data because that doesn't actually use all the data in the right way. And of course, like this is not probably going to be robust to noise because the neural network could actually be getting points wrong because they're noisy. And then now if you're kind of upweighting them in this way, like you could actually make it worse. So I think there's obvious problem. Like how do you make sure whether something is actually an interesting pattern or something is just noise? And I want to conclude with sort of, like even if we had diverse data, things are bad, but like could we ever get diverse enough data? So a lot of research in neural networks right now is just going along this path of let's try to get as much data as we can. And so now we've been able to not use labels. And so they have this so-called self-supervised learning where you can just give a lot of raw data that you obtain. And so that's a potential path to get a lot of diversity because you can literally train on any data that you can find. But like, we don't know if this actually contains kind of all these interventions in some sense that you should actually hope your model to learn so that it doesn't learn these kind of correlations. And even if you have diverse data, that's already like, we have to also figure out how to use the diversity. But like, this is obvious question of, can we ever hope to get diverse enough data? And I think like the fact that subsampling was, kind of worked pretty well, got me really interested in thinking more about active data collection. And I keep thinking about, is this the way forward? Because right now we just like collect data passively. And so we are not really, we are kind of hoping the network learns something from the tails, but like you're not really, collecting them more carefully. And so, I wonder if active data collection is a way forward. And also if you look at kind of the psychology experiments and how like we as humans learn by actually interacting with the world and like doing experiments on our own to figure out like what actually happens when you make certain changes in the world. But a lot of the like neural network training that we have right now is very different where we just give a lot of passive data. So as we get more agents to like kind of interact in the world and think about active data collection, I think that could be really important. And we shouldn't be going down the path of just trying to give as much data as we can find to the models, which is kind of what a lot of research is doing these days. With that, I'll stop and thank Google and Open Philanthropy for supporting all this work and my wonderful collaborators.
Maybe a quick question. Maybe just for those of us who are very naive about these things, what's the difference between subsample? It sounds to me like increasing weights on the small set that you care about is morally, if not completely, technically equivalent to subsampling, and I couldn't understand why these are quite different.
Yeah. So I guess that's the point where like the neural network things matter, which is that if you have a lot of capacity and you have this really large model, so it can still do degenerate things on certain data points, which like even if you upweighted the point, it doesn't matter. So if you have a large model, just because it has low loss on a point doesn't mean it's actually learned the point. So I guess that is why the two things are different. So if we did subsampling, now so why the model does the issue in the first place is that if your 90% of your training data can be classified by the like a linear boundary, like by the background, the model is just going to learn them. And then you have upweighted, so it will fit those other points, but it will not really generalize. But if you had subsample, now there's like only 50% of the data points that could actually be covered by the background. So the model is no longer going to use only the background and has to do something better. So that's why subsampling matters. So I think the core point is that low loss does not really mean anything when you have a large network because of the capacity issue.
Do you think that the optimization, like if I'm doing batches and 99% of the batch is one type of data and 1% is another, like even if I'm weighting them differently, could that be changing like the implicit bias?
Yeah, people have tried a lot of these things. They like couldn't get any conclusive results. So it does change things a little bit, but like not, it's not like it doesn't really solve the problem. Yeah. So that's a whole other beast. Like it's a, I mean, yeah, there are a lot of small things that change results too. But yeah, but just changing the batch doesn't help.
You should let the next speaker sit up.